Good morning, everyone. Thank you, Fred, for that nice introduction. I can tell you that doing chemistry in Amsterdam is a lot of fun for many different reasons. So is doing astronomy here in Arbor, actually. It's a pleasure to be here. I hope everyone is having a good time today. Thank you for coming out here in the cold weather and hear what I have to say on the origin of water here on Earth. So let's get started on that. Water is something that we really see everywhere here on Earth. It may have been on your car this morning as ice to get scraped off the windows before you can come here. It's vital to all life. The human body consists of about 70% water. And pretty much every organism on Earth that we know of needs water in one form or another to live. Water is important also for many other aspects of our daily life. We can use it to heat and cool our homes, our offices. We use it for transportation, shipping goods around the world, for sanitation, or just for fun to go for a swim or whatever. Water really is important. It's everywhere. And that begs the question, where does it come from? Because we take it for granted that when you turn a faucet, that water comes out and we can figure out where that came from. But the water on Earth on a global scale, where did that come from? Was that part of the Earth when the Earth formed 4.5 billion years ago? Or did it come from outer space in the form of maybe comets, asteroids, and meteorites? And that's the question that I want to address today. So what I'm going to talk about is, first of all, we need to know how much water there is on Earth and some of its basic properties that we can use to answer these questions about its origin. And that means we also need to talk about how the Earth formed. So this is also going to be a talk about our own interstellar origins as a planet and as a solar system. We're going to look at the interstellar origin of water, how water is formed out in space, and how it gets delivered to a young star and to the planets that are forming there. And then I'm going to address the main question, where did the water on Earth come from? And the two main hypotheses that I'll talk about are either wet formation, meaning that when the Earth formed, it formed with all the water that we currently have. Or the other option, external delivery, where the Earth formed basically as a dry planet, and then the water got delivered at a later stage. So let's start by talking about how much water we have on Earth. And that may be a number that you find surprising. The water that we see on Earth is mostly in the form of salt water. That's in the oceans, the seas. And normally we think about having 5 oceans roughly. We have the Atlantic, the Pacific, the Indian Ocean, a couple more. But if we flatten out the entire Earth as a single map, then we do see that all that water is connected. So for simplicity, we're going to call this one ocean. All the salt water that we have on Earth is what we're going to call one ocean. Would anyone care to guess how much water we have in our rivers and lakes compared to what we have in oceans? Does anyone have an idea? It's very little. That's a number with a lot of decimal zeros. Insignificant compared to the global budget. There's also quite a bit of water stored in ice, actually, much more than in those rivers. But it's still only about 2% of what we have in the ocean. So it's still not really anything that adds to the total number. We know there is water out in the sky, in clouds and rain and everything. That seems like a lot sometimes, excuse me, if you're outside and trying to get to a dry place. But altogether, it really isn't anything at all. It's like 1 part in a million if we compare that to what we have in oceans. Another reservoir of water on Earth is in underground locations, just water in the soil under our feet. That actually, if you count up everything on the planet, amounts to a reasonable amount. It's about 16% of the total water that we have in oceans. And then we can dig down deeper into sedimentary rock. And there we find another reasonable fraction. Now we're up to about 20%, 25% of what we find in an ocean. That's actually quite a lot. If you think about rocks, you don't think about rocks as holding a lot of water, right? Rocks are rocks. But if you look at rocks on a molecular scale, it's definitely possible to trap quite a bit of water in those rocks. And on a global scale, that amounts to about 25% of all the water we have in the oceans. All right, so by now we're up to 1.5 total oceans, maybe. But we can go even deeper. If we go into Earth's mantle, we have the upper mantle, the lower mantle, and Earth's core. The upper mantle, it's not entirely clear because it's hard to measure how much water there is, so this is mostly in theoretical estimates. But it's about between 10% and 50% of what we find in the oceans. The lower mantle, even more variation in various different calculations, ranging from 10% of the oceans to about 2 times what we have in the oceans. Would anyone care to estimate how much we can have in the core? You say 3, right? Okay, 0, yeah. Well, you know, any number you could have mentioned would possibly be correct. Estimates vary wildly on this topic, and it's, you know, it's not hard to figure out why it's difficult to estimate this. This is deep down under our feet. We can't dig down. We can't measure it directly, so it's really based on theoretical calculations and maybe some seismic measurements. But estimates range anywhere from no water at all to as much as 100 times all the water that we have in our oceans. That's, you know, a mind-bogglingly large number. And the problem with a number like that is if we want to understand where the water on Earth comes from, we need to know its basic properties, right? We can talk about things like the deuterium fraction, which we'll get to at the end. But that means we need to measure those properties. And we can do that in the water that we have in the oceans. But we cannot do that if there is enough water to fill in another 100 oceans stuck in the core. We can't get at it. We do not know what kind of properties there is that water has. And that makes it very difficult to figure out where that water may have come from, because we don't know its properties. All right, so to summarize that, the typical numbers that people go with is that we have about 3 total oceans worth of water on Earth. That's the best estimate out of between 0 and 100. Does that mean that Earth is a wet planet? Well, again, it depends on when you're looking at it. If you're outside biking or walking through the rain, as we tend to do a lot in Amsterdam, then it seems like an awfully wet planet. But if you look at the total fraction of mass that is hidden in water, it's really not that much. It's only about 0.1%. And this is a nice visualization of that. If you take all the water that we have in our oceans and whatever we may have in the mantle, maybe in the core, and you take that into a little ball, you get something like that. It's about the size of the moon, I think. That gives you an idea of how dry the Earth is as a global total composition. All right, so we need to compare this to the rest of our solar system. So let's just go through the planets one by one. We have Mercury in the top left. There are some indications that there may be some water ice on Mercury near the poles, hidden from irradiation from the sun, but it's really not that much. On Venus, there may have been liquid water in the distant past, when Venus was first formed. Right now, if there is any water vapor, if there is any water at all, it's vapor. It's completely evaporated and just floating around in the atmosphere. On Earth, obviously, we have liquid water, ice, and water vapor at about 0.1% of the total planet mass. There is some water ice on the moon, again, some deposits at the poles. On Mars, ongoing question, all these Mars rovers and other robots that we send out there, all of them start looking for water when they're there. There was probably liquid water on Mars in the past, but again, all of that is gone by now, and any water that remains only exists as ice or as vapor. The atmospheric pressure on Mars is simply not high enough, like it is here on Earth, to even have liquid water on the surface. All right, so those are the 4 rocky planets. There is probably some water on all of them, but it's a very tiny amount compared to the total mass of those planets. Now, if we look at Jupiter and Saturn, the planets themselves, we don't really know. It's very hard to get an estimate of whether there is water at all. But we know that on some of the moons around Jupiter and Saturn, there's actually quite a lot of water. Europa and Titan both have significant amounts of water, mostly as ice, but those those moons may also have subsurface liquid oceans of water. And that of course, brings to mind all kinds of interesting possibilities with whether there may be life on those planets hidden beneath that ice, and we hope to find out one day. We don't know at the moment. But there is most definitely water on those moons. And then we have our 2 final ice giants, Uranus and Neptune. And the simple fact that they're called ice giants may indeed suggest that there is water frozen in those atmospheres, and that does seem to be the case, again in quite large amounts. Again, to give you an impression of how much water ice there is on some of these moons, these are Europa and Titan orbiting Jupiter and Saturn respectively, and again the Earth. That's again, if you just take all the water that we think is present on those 2 moons and make that into a single ball, that's about how much it is. And if you compare that to the Earth, you see Earth is only that tiny amount up there. The relative amount of water on those 2 rocky moons is much bigger than the amount of water relative to what we have on Earth. And that provides a very important clue to the origin of water. If we put this in a graph like this, I'll walk you through this. This shows as a function of distance from the sun on the horizontal axis. It just shows the planets we have in our solar system. Mercury in the bottom left, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. And what I've shown here is the percentage fraction of ice in each of these planets and the percent of rock in each of these planets. The rocks are shown with the yellow symbols, and the ice are the orange symbols. So you can see that for the 4 rocky planets, Mercury, Venus, Earth, and Mars, there's very little ice. These orange labels are all in the bottom left of this plot. And they're almost completely made out of rock. And then if you look at Jupiter and Saturn, they have slightly larger fractions of ice. And then Uranus and Neptune have really substantial fractions of ice, up to 60% or so. So there is a very strong increase in the potential amount of water ice going from the rocky planets in the inner part of the solar system out to the giant planets in the outer parts. All right, so if we summarize what we have so far, Earth has about 3 total oceans worth of water, 1 ocean floating around the surface, and about 2 more stuck in the core. That's a fairly low water content if you compare it to the total mass of the planet. And we find a much higher water content for the moons around Jupiter and Saturn, and also for the ice giants, Uranus and Neptune. So how can we explain this? If we want to answer that question, we need to know how these planets were formed. So we're going to look at stellar birth. This is a gorgeous picture, not taken by myself, grabbed off the internet. This is Lake Luzern in Switzerland. And what you see up there is the Orion constellation. It has the 3 stars horizontally aligned. That's Orion's belt. And then below that, a little bit to the left, you see the Sword of Orion. We're going to zoom in on that Sword of Orion, because that is a stellar nursery. It's that pink fuzzy blob. And if we take the Hubble Space Telescope or another good telescope on Earth, that's what that fuzzy blob looks like. You can see the Orion Nebula with your naked eye on a very good, clear night. But that's what it looks like with a telescope. Now we're going to take a tour through this stellar nursery. And I should point out that animation is based on actual astronomical observations, but obviously we cannot fly around the Orion Nebula with a telescope. But if we could, it might look something like this. Slightly different colors this time. I'm going to zoom in it and just go around. And all these points of light that you see here, for the most part, are young stars that are currently being formed. And you see that some of them appear to be surrounded by some fuzzy blob of material. That's basically the cocoon out of which they're being formed. We're going to look at one of these in details, like a little tadpole with a tail wiggling. And if we let some of that material evaporate away, then we see this. We see a disk, and we see a jet blowing out on either side. We'll have another look at one of those. We're supposed to have another look at one of those. Yes, there we go. All right, another one of those blobs. And this one will go into more detail into that disk. That jet of material is now going up and down. And that's what we're left with. That's how we form a solar system. You get a disk like that. I'll talk about it a little bit more in a moment. Just let this run. And now we're seeing that we're forming planets. And we have the sun right there. I think we had Saturn. There we go, Saturn zooming by. And there we have something that looks a lot like our own blue little marble. All right, so let me talk about that a little bit more, how we form stars and planets. It's like a universal cycle of matter. The universe is really good at recycling. No material ever goes to waste. It goes into stars and planets at some point, but those will come to an end at some point and then get recycled into new stars and planets. So we start at the top here. There we have something labeled a dense cloud. The universe, the Milky Way, is quite full of these. And so are other galaxies. These are giant clouds. They can be a couple of light years across, really enormous sizes, very massive, typically enough material to form many hundreds or thousands of suns. And at some point, there may be an instability in one of those clouds, and then gravity starts to take a hold. And we all know what gravity does. It likes to pull things together. That's how we're standing on Earth. The Earth likes to pull us towards the center. That's also how the Earth rotates around the sun. It gets basically pulled in on that circular orbit all the time. So we get that instability in one of these clouds, and gravity takes over, and then material starts collapsing and becomes denser and denser and denser, up to the point where it gets so dense that it basically starts to, you get fusion going, and that's when you start the star, really. But at that point that you start that star, where you get the fusion going, you still have a lot of material left over. And that material, usually there's some amount of rotation. And again, because of the rotation and the gravity, that material starts to flatten out into a disk. It's like you get a pancake around that central star. And it's in that disk where the leftover material is going to, again, collapse together or get together, partially by gravity, and form planets. And that's where we're left at the bottom right with that stellar system and the planets and the solar system like we know it. And then to complete that universal cycle of matter, at some point the sun and any other star will come to the end of its life. For the sun, that's fortunately going to take another 5 billion years or so. It's not something we have to worry about. But when that happens, it's partially going to blow away a lot of the material that it started out with. It's going to be blown out into interstellar space, and it may float around there for many billions of years before it kind of gets together again into these new kinds of clouds, and then the whole cycle can start anew. All right, how do we know all of this? Astronomy is like 10 parts actual science and certainly 1 part imagination, and sometimes maybe more parts imagination. People thought of this at some point, and we have very clear evidence in our own solar system, certainly of the presence of that disk, because we know that all the planets, almost all the planets, lie in that neat same plane. And there's other things in our solar system that we can look at. There's the asteroid belt between Mars and Jupiter. There's also the Kuiper belt, the blue circle here at the outer end, where we find a lot of debris, a lot of small rocky bodies that we think are leftover remnants from when we had that actual disk. So that's our disk, but I said that the solar system formed out of a cloud. Is there any evidence of that cloud? Well, yes, there is. That is called the Oort cloud. That goes on much larger scales. If you look at that tiny little blue box here at the center, that's the size of our own solar system. And that cloud, this sort of cross-section that you see here, is much larger. That spans a good distance of a good part of the distance to the next star, the next nearest star. And that Oort cloud is comprised of billions of comets. And all those comets are basically tiny balls of rock and ice that float around there, are in some sort of very wide orbit around the sun. And we think that certainly the shape of that suggests very strongly that we once had our own roughly spherical ball of gas and dust out of which we formed. All right, so that star formation scenario that I was talking about, where you have the gravitational collapse, you form the star, you get that disk of material in which you form the planets. There's a lot of observational evidence for that, both in our own solar system and also simply looking at other stars. All right, so we have that low water content for the rocky planets in our solar system and a higher water content for planets farther away from the sun. And we know that stars form in giant clouds of gas and dust, and that the planets then form in a disk around a young star. So we need to tie that together. We need to look at the interstellar origin of water. And in order to do that, we need to figure out how we can observe water in space. What do I have here? How do you know it's water? How do you know it's glass? You know, I'm holding some solid object that is shaped like a glass, and there is a clear liquid inside. And I can taste it. I confirm that it tastes like water. But we can't do that with water out in space. If we think there's water out in space, well, it's not going to be in a glass. It's going to be floating around in some. Do you have a question?
Yeah, well, because when it looks like water, who knows what it could be? Phosphoryl chloride?
Well, there are many liquids that we know on Earth that are clear and basically look like water. And on Earth, you could test that. You could take a sip of it. If it's a toxic liquid, you may not want to do that because that might be the last sip you ever take. But you know, it's fairly simple. If we have a substance on Earth, we can take it to a lab and we can run all kinds of tests on it. We can measure its density. We can look at at what temperature it evaporates or what temperature it freezes, which for water would be a really strong indicator because we know at what temperatures water is supposed to freeze and evaporate. But again, we can't do that with water out in space. So we need to play a different trick. We need to use telescopes, obviously. That's what we always do in astronomy, right? We take a telescope, we point it up in space. And the good thing about telescopes is that we can use a very wide range of frequencies or wavelengths to study objects in space. We're all familiar with visible light, right? That's how you can see what's on this slide. That's visible light. And that is a tiny part of what is called the electromagnetic spectrum. And that tiny part is that little ring of colors here at the center. We can go to much shorter wavelengths. Light is a wave, has a wavelength, and a frequency at which that wave vibrates. If we go to shorter wavelengths or higher frequencies, we go to ultraviolet light first. That's what comes out of the sun in part. That's how you get a suntan in summer. We can go to even higher frequencies, X-rays and gamma rays. X-rays are used in hospitals to look basically through your body and see your bones. Or we can go the other way. If we start at visible light and go to longer wavelengths, we can go to the infrared, we can go to microwaves, and we can go to radio. Now, if we talk about astronomy, we have telescopes that can operate at all of these wavelengths. And that gives us a vast amount of information on whatever object out in the sky, out in space that we want to look at. For water specifically, there's no point in using that entire range. What we typically do is look at vibrations or rotations of water molecules. A water molecule, as it is drawn here schematically, consists of one oxygen atom that we typically draw in red. And it has two hydrogen atoms that we draw either in white or in black, depends on who makes the drawings. And they're tied together like that, so you have the oxygen atom in the center and then the two hydrogen atoms dangling off. And they can vibrate in all kinds of different ways, and they can rotate in all kinds of different ways. And those vibrations and those rotations provide a very specific fingerprint of a water molecule. It's like a barcode. We can take our telescope, point it up at some cloud, some young star, and we can measure the spectrum of light that comes from that star. And that spectrum of light is essentially a barcode, and we use our telescope as a barcode reader. And that tells us the chemical composition of that cloud that we're looking at. If we see very specific lines in that spectrum that we know from laboratory work on Earth that correspond to vibrations of water or rotations of water, then we know that there is water. The other thing about going to longer wavelengths is that we can sometimes see much more in any case. What you see here on the left is a visible light image of a cloud called Barnard 68. It's a very well-studied cloud, very well-known cloud in astronomy circles. It's a very cold cloud. It's like 400 degrees below 0 in Fahrenheit or 10 Kelvin. And that cloud has probably enough material to form at least one solar system. And it's going to take a lot of time before it gets around to doing that, but we know from measurements that it can do that. Of course, if you look at it in visible light on the left, you don't see all that much, right? It's just a black blob. If we go to infrared wavelengths on the right, we can actually see through that cloud. The cloud is still there in infrared light, but we can see background stars. And that means we can use those background stars as a kind of lamp that we let shine through that cloud, and then we can use something called absorption spectroscopy. The material in that cloud is going to absorb some of the light, some of the infrared light that comes from those background stars, and again leave that very specific fingerprint in the spectrum that we observe. And that is something we can use to determine whether there is water there or not. All right, so we need telescopes to do that. We can use, for example, the very large telescope in Paranal in Chile, South America. Beautiful instrument that I worked with once myself. Or we can go to Mauna Kea on Hawaii and use the James Clerk Maxwell telescope, the one indicated with that yellow arrow. Works at even longer wavelengths. That's another place I've been. You can see that it's not so bad being an astronomer, right? You get to go to Amsterdam once in a while, or you get to go to Chile or Mauna Kea. It's all fun to go there and just spend a night or a few nights at one of those telescopes. But there's a problem. If we want to do this from the ground, and we want to observe water in space, there's a problem because there's water up in our own atmosphere, right? And that's going to block a lot of that light that we may want to use to determine whether there's water at all. If we are talking about a very specific fingerprint in a spectrum, but we're looking through the atmosphere where we know there's water, then obviously we're going to find that fingerprint everywhere because there's always water in the atmosphere. So it helps to go to mountains. That's why we put these telescopes on Mauna Kea and not here in Michigan or in Chile, where there's also a very dry, high mountain. But even then, there are some parts of the atmosphere that are always going to be opaque, where the light just doesn't shine through. And that is shown here, again, we have the visible part of the spectrum, that rainbow of colors in the center. That's fine. Visible light, we know, comes through the atmosphere, because otherwise we wouldn't see stars ourselves. If you go to much longer wavelengths, radio, that's fine as well. That filters through the atmosphere for the most part. But most of the wavelength regime in between, where we have those vibrations and those rotation lines of water, the atmosphere blocks out a lot of that light. All right, so you can figure out what we need to do. We need to go into space. And that's why we spend so much money putting telescopes in space, because we don't have to worry about the atmosphere up there. And there are there are more than three actually, but I'll show the three telescopes here that have been used most recently to measure water in space. There was the submillimeter wave astronomy satellite, or SWAS for short, that started out in 1998 and worked until about 2004. There's the Spitzer Space Telescope that was mostly good for looking at water between 2003 and 2009. Actually, the Spitzer telescope still works, but maybe not at the wavelengths anymore where it can observe water. And then most recently, we had the Herschel Space Observatory, not the Herschel Space Telescope, that was launched in 2009 and came to the end of its mission earlier this year in April. Those three telescopes have taught us a lot about water in space, have taught us a lot about the interstellar origin of water, and have been crucial in really trying to help us answer these questions about water, where the water on Earth comes from. All right, so now that we know how to observe water, let's go look for it. I'm going to show you a bunch of astronomical observations, water spectra for the most part, in some of these different stages of star formation. I'm going to start with one of those dense clouds at the top, and then I'm going to work my way towards a disk where we're currently forming planets, and then we'll end up with possibly a new stellar system. This spectrum here, it doesn't look like much, but to us astronomers, this got us really excited. This is a spectrum of cold water in a cold cloud. And by cold, I mean something, again, like 10 Kelvin or something like minus 400 Fahrenheit. It's really cold. You would expect water to be completely frozen out at those temperatures, right? We're way below the freezing point of water. But there is a tiny amount of water still present as vapor there. And that is basically because there is actually a lot of water ice in this cloud as well. But there are also UV photons. And those UV photons bombard the ice all the time. And each UV photon can basically kick off a water molecule and get it into the vapor phase temporarily. And that's what we see here. This is, this was a measurement done with the Herschel Space Observatory, and was really the first time that we saw cold water vapor in that very early stage where we have a dense cloud and don't even have a star yet. If we take the next step in the star formation sequence, we go to a cloud that does have stars already, and this is back to the Orion Nebula, where we were zooming through with our fancy telescope camera earlier. And now we see a much stronger signal. This one was still fairly weak. You can see that there is something. But this is a much stronger spectrum. And in fact, if you basically count the number of water molecules that you need to get a signal of that intensity, it amounts to about 1 million oceans worth of water. So in that single cloud in Orion that may go on to form a single star, maybe like our own sun, we have enough water to fill Earth's oceans 1 million times over. Excuse me. We can also use water as a kind of motion sensor or as a thermometer. And that's what I'm showing here. This is again in one of those clouds where we already have a star. We have material swirling around it, and we have that jet going out in both directions. These are more Herschel observations from 3 different very young stars. And in all cases, what we see is, again, more water. I didn't calculate how many oceans this is, but it's got to, again, be a lot. a few 100,000 probably at least. The other thing, if we look at these spectra, there's a couple of things that you can see about it, right? You have an intensity, how high it is basically, that tells us something about how much water there is. But there's also the shape of these spectra, especially whether they're very narrow or very broad. And that tells us something about the velocity at which this material is moving. And what we can see here is what we call outflows. That is material that is moving at many thousands of miles per hour, or hundreds of thousands of miles per hour, shooting out into interstellar space. And that is associated with the jet that you may remember from the animations that we had. And we can actually make water maps of one of those jets. That's what I've got here. On the left, we have an image taken with the Spitzer telescope. On the right, we have an image taken with the Herschel telescope. The one on the left doesn't show water as such. It just shows the general structure that we have. So what you see, there's that dark lane here at the center with the brightest point in the middle. That bright point is where we are forming a young star. And that dark lane of material is kind of that disk where we're going to form the planets. And then going north-south, going up and down, we have that strong jet of material being blasted away by the young star out into space. That's what we see in the Spitzer image. If we look at the Herschel image on the right, those green and yellow and purple blobs, that's all water. It's not as pretty as the Spitzer image, but it does show us that there is an enormous amount of water in that very fast-moving material. And we can measure the velocities at which this is moving, and that's about 100,000 miles per hour. That's fast, right? It also means that this water is lost to space. This is not going to make it onto any kind of planets. It's just being blasted away. All right, so what have we learned from that? We know that young stars are born in these very cold clouds of gas and dust, 10 Kelvin, minus 400 something Fahrenheit. We can see with our infrared space telescopes that water is present as vapor and as ice. And we can see that if we measure the intensity of those water spectra, that we have enough in a typical single cloud to make a million oceans. And we see hot water vapor being blasted away into space. That's not going to make it towards planets. But at the same time, we see evidence for water ice that does get delivered into that disk, and that may actually make it to planets. So this was still these clouds where we are forming the stars. Now we need to look at the disks where we are forming the planets, because ultimately we want to know how the water came to Earth. And again, we have Herschel observations of water ice in a disk. Again, it doesn't look all that impressive maybe to the naked eye, but it got us as astronomers, again, very excited that we saw this. It's in the blue circle there, that little blip on the spectrum. That's an indication of the presence of water ice in a young disk. And when I say young, I still mean a million years old. But by astronomical perspectives, trust me, that is still very young. And again, we can measure how much water there is in this one. And now it's about 75,000 oceans. So it's not a million anymore, but that's because we're no longer looking on the total cloud scale. This is really just the water that is in the disk that may actually make it onto planets. 75,000 oceans is still a lot of water and enough to make some planets out of. We have more indications of water ice in disks. This is at a different part of the electromagnetic spectrum. Now you see water ice in absorption, along with a couple of other compounds like carbon monoxide and carbon dioxide and silicate dust. But again, strong indications of the presence of water ice. We also see cold water vapor in some of these planet-forming disks. And again, that is something we had kind of expected to see for the same reason that we saw the very cold water vapor in these cold clouds. Also in a disk, you have the star that is illuminating the surface of the disk. And those UV photons coming from the star can again hit that water ice and break it out into the vapor phase. And that's something we see in this disk called TW Hydra, a little bit older than the disk I had earlier. This is about 3 million years. So it's well on its way to actually forming planets, probably at least getting planetesimals. And now what we see in the vapor phase, not that much water altogether. It's about 0.005 oceans worth of water. But that's indicative of 6,000 oceans worth of water ice. And it's that water ice, again, that is important for forming the planets. One more indication of water vapor, this time hot water vapor. So it's different than the cold water on the previous slide. This is again in AA Tau, the star I showed a little earlier. And this is hot water vapor very close to the star. This is within 1 astronomical unit. And 1 astronomical unit is the orbit of the Earth. So if we look at one of these very young disks currently forming planets, and we look in the innermost part, comparable to the orbit of the Earth, that's where we see a lot of hot water vapor. But we don't see any ice at those very close-in radii. The ice is detected much further out. And that gets us to some important conclusions about the distribution of water in such a planet-forming disk. All right, so now we have a schematic, basically a cut through part of the disk. We have the star on the left, and the star is shining onto the surface of that disk. And that's going to heat up the surface. So we have a disk with a very hot top and bottom. But towards the center of the disk, in the middle, it's much colder. Now, if we look at how the water is distributed in that, based on all of those spectra that I was showing you, in the very innermost part of the disk, we have material that is very rich in water vapor, hot water vapor. Further out, the water is mostly frozen out. So somewhere in between, we get a transition from water being in vapor and water being ice. And that is what we call the snow line. And the snow line is an important concept if you're looking at water in disks. It kind of tells you, it tells you where you have the water ice and where you have the water vapor. And now we need to compare that to the planet compositions that we have in our own solar system. You'll remember this plot from earlier, where I was saying that if you look at the percentage of ice in the rocky planets, Mercury, Venus, Earth, and Mars, on the bottom left, tiny fraction. But if you go out towards the ice giants in our solar system, you get a much larger fraction of water ice. So how does that all tie together? All right, we know that planets are ultimately formed out of submicron-sized dust grains that coagulate together and slowly grow toward larger and larger grains, rocks, all the way up to planets. Inside that snow line, there's no water ice. The rocky material, that dust that we're building planets out of, does not have any water in it. It's just pure silicate or carbon dust. But if you go outside the snow line, there you have a lot of water ice on those rocky grains. In our own solar system, when it was forming, the snow line probably lay somewhere between Mars and Jupiter. So if we look at the formation of the Earth, the material that the Earth formed out of, that was inside that snow line, there was no water ice present in those grains. There was water vapor there, but that doesn't matter so much for forming rocky planets, because we really need just the rocky material. So this means that the Earth most likely formed dry. There was very little, if any, water at all present as ice on the material that the Earth formed out of. All right, so if the Earth didn't form with any appreciable amount of water on it, we need to have gotten it from somewhere else. And there are good indications of where that may have come from. The Apollo mission, for example, looked at the moon and found that the moon was hit by numerous 10 to 100 kilometer sized bodies. That explains all the craters that we see in the surface of the moon. In that phase of impact, is something known as the late heavy bombardment. And I'll tell you why it was late and why it was heavy. The important point is, if this happened on the moon, it must have happened on Earth too, right? Because we're close together in the solar system. And the important point is that Earth's cross-section, you just look at the size of the planet, is 20 times bigger than it is for the moon. So that means that we were hit by roughly 20 times as much material. We don't see so much evidence for that on the surface of the Earth because we have plate tectonics and whatever craters we had are mostly filled in and moved around and everything. But it must have happened. And there are all kinds of interesting numerical simulations, computer simulations, that simulate that phase of bombardment. There's one in particular called the Nice model, named after the city in France. It is also actually a nice model because it does explain a lot of what it shows. And the simulation I'll show you here is sort of a top-down view of the solar system. We have the sun at the center here. We're going to start out with Jupiter's orbit in red. You'll see the orbits of the other gas giants coming in as well. And then there's going to be the Kuiper Belt. And that's a reservoir of basically these 10 to 100 kilometer sized asteroids. And that simulation is going to run. It starts at t is 0, basically the birth of the solar system. And then it's going to show you how some of these planetary orbits and all of these asteroids are going to interact together. So we have the orbit of Jupiter, we have the orbit of Saturn a little further out, we have Neptune, and we have Uranus. You may note that these are not in the order in which they currently are. Those are all the asteroids, and then we're going to start the clock running. And yeah, this looks very stable at the moment, but keep your eyes open, it's going to slow down, and boom. That was the late heavy bombardment. There was something, we think, in the early phases of the solar system where the giant planets seemed to be stable for a few 100 million years, but then there was some instability that arose. We don't quite know how that happened. And that basically kicked up all the smaller material in the solar system. It kicked up all these asteroids into all kinds of weird elliptical orbits flying around the solar system, and a lot of those hit the Earth, as well as Mars and Venus and Mercury and the Moon and everything. This also led to the orbits of those giant planets shifting, and now you see that they're in the order in which they are today, with Neptune furthest out and Uranus further in. But there are strong indications from these simulations that those two planets started in basically in opposite directions. All right, so from that late heavy bombardment, we know that the Earth was hit by a lot of material when it was only a few 100 million years old. Now we need to figure out whether that can indeed bring a lot of water to the Earth, and more computer simulations of that show that that was indeed possible. What you're going to see here, this is another simulation of what happens in the solar system. This is on slightly smaller scales. On the horizontal axis, you see the radius of the orbit in astronomical units. Again, 1 AU is the orbit of the Earth. Venus is at about 0.7, the V there, and Mars, MA, is at about 1.5. The big black blob you see in the bottom right, that is Jupiter, at about 5 astronomical units. On the vertical axis is plotted the eccentricity, and eccentricity basically means how round an orbit is. If the eccentricity is 0, the orbit is completely circular. If the eccentricity is high, towards 1 or 0.8, you have a very elliptical orbit. And then you see something with color. That bar at the bottom tells you how much water there is in each of these little bodies that we have in our early solar system. Red means that the material is completely dry. Yellow means that there is a little bit of water. Blue means that there is quite a bit of water. All right, and all these little dots are roughly moon-sized planetesimals. We think that in the early solar system, there was a distribution of these rocky bodies, and those then further coagulated gravitationally to form the actual planets. All right, I'm going to start that simulation, and now what you see is they get all jiggery. That basically just means they're moving around at weird orbits in the solar system. But in the bottom left, you see some of these dots getting bigger now. And you also see the color is changing for some of them. We now have one that is turning orange. We have one there that is doing green. The blob at 1 AU is now turning orange, yellow, green, all the way going up to blue. And you also see that the total number of dots is going down. And now as we get towards the end of this simulation, we are left with something that looks roughly like the solar system. We have that blue blob at 1 AU, that's the Earth. We have a greenish blob a little closer in, that is roughly Venus. And then we have something out at 2 AU, which is supposed to be Mars. All right, so it's not a perfect representation of the solar system. Venus is a little too close to the sun. Mars is a little too far away. Mars is also a little too heavy. But as a sort of general scheme of what may have happened, computer simulations like that do a fairly good job of getting the big picture correct. And you may also have noticed as the colors were changing, we started with all red material at around the region where we currently have the Earth. That's because of that snowline issue. There simply wasn't any water ice in there. But then as that simulation ran, the color changed because we got material from further out in the solar system that did have a lot of water ice hitting the Earth during that late heavy bombardment and depositing all that ice on our planet. And that brings me to my summary. We talked about how much water there is on Earth to begin with. That is about 1 ocean on the surface and then 2 or more deeper down. In the solar system, we have a low water content for the rocky planets and a higher water ice content for the gas and ice giants. And that is something we can explain by the distribution of water vapor and water ice in planet-forming disks that we can currently see with these telescopes that we have out in space. As to the origin of water on Earth, we're pretty sure now that the Earth formed completely dry because it formed at a place in that disk where there simply wasn't any water ice available. But then we had that instability in the solar system, in the orbits of the gas giants that kicked a lot of asteroids into the inner solar system, caused the late heavy bombardment, and those asteroids carried a lot of water and delivered it to the Earth, and that's why we have this nice blue planet out here today. Thank you very much.